We're continuing with Chapter 10, Geometry. In this chapter, we're going to examine triangles. Objectives: solve problems involving angle relationships in triangles, solve problems involving similar triangles, solve problems using the Pythagorean theorem. A triangle is a closed geometric figure that has three sides, all of which lie on a flat surface or plane. Closed geometric figure means if you start at any point and trace along the sides, you end up where you started. Euclid's theorem. A theorem is a conclusion that is proved to be true using deductive reasoning. Euclid's assumption. Given a line and a point not on the line, one and only one line can be drawn through the given point parallel to the given line, as you can see in the figure below. You're given the line that's at the bottom, you're given a point, you can only have one line through that given point that's parallel to the given line. So continuing with Euclid's theorem, the sum of the measures of three angles of any triangle is 180 degrees. And we're using the relationships that we saw with respect to parallel lines and the angles formed by a transversal that cuts through the parallel lines to determine this. We've got our two parallel lines. We've got a triangle, A, B, C. You can see that we have labeled the different angles. So we want to show that the sum of the measures of the three angles of any triangle, 1, 3, and 5, is 180 degrees. So here's a proof. The measure of angle 1 is equal to the measure of angle 2, and the measure of angle 3 is equal to the measure of angle 4, alternate interior angles. And we can refer back to the diagram. One and 2 are equal. 3 and 4 are equal. Angles 2, 5, and 4 form a straight line, which would be 180 degrees. So we have the measure of angle 2 plus the measure of angle 5 plus the measure of angle 4 is equal to 180. Angles 1 and 2 are equal. We already know that from above. So we're going to replace the measure of angle 1 with the measure of angle 2 with the measure of angle 1 down below. Same with the measures of angles 3 and 4. We're replacing the measure of angle 4 with the measure of angle 3. So this tells us that the measure of angles 1, 5, and 3, which are inside the triangle, would be equal to 180 degrees. In this example, we're going to use angle relationships in triangles. We want to find the measure of angle A for the triangle ABC. We know that the measure of the three angles is equal to 180 degrees. We're given the measure of two of the angles, 120 and 17. So that tells us that the measure of angle A plus the two measures we're given would be equal to 180. Measure A is equal to 137, which is the sum of 120 and 17, is equal to 180. Solving for the measure of angle A, we get 43 degrees. And you can check this by adding the three together. That will give you 180 degrees. Example 2. Find the measures of angles 1 through 5. Okay, well, the measure of angle 1, angle 2, and 43 degrees would be equal to 180 because they form a triangle. We also know that the measure of angle 1 is 90 degrees because of the little box at the vertex. That tells us that all four of those angles are 90 degrees. So we can substitute 90 degrees for the measure of angle 1. That gives us 90 degrees plus measure of angle 2 plus 43 degrees is equal to 180. And solving for the measure of angle 2, we get 47 degrees. So now we know the measure of angle 2. That is going to give us sufficient information to find the measure of the other angles, because angle 2 and angle 3 are vertical angles. So that tells us that the measure of angle 3 is also equal to 47 degrees. And that we're going to show that on the next slide. That is this top part. The measure of angle 3 plus the measure of angle 4 plus the measure of plus 60 degrees is equal to 180. So we substitute 47 degrees for the measure of 3. Solving for the measure of angle 4, which we don't know yet, we get 73 degrees for angle 4. Again, using our relationships that we know, the measure of angle 4 and the measure of angle 5 has to be equal to 180. The measure of angle 4 is 73 degrees, which gives us the measure of angle 5 is 107. We classified angles by their size, and we can do the same thing with triangles. And an acute triangle means that all of the angles are acute. They're all less than 90 degrees. In a right triangle, one angle equals 90 degrees. That means that the sum of the other two is equal to 90 degrees. And an obtuse triangle, one angle is obtuse, which means it's greater than 90 degrees but less than 180. We can also classify them by sides. An isosceles triangle has two sides that are equal. The angles opposite these two sides also have the same measure, and we indicate that the sides are equal by drawing a little line on each of them to show they're equal. Same with the measure of the angles. We show that the angles are equal by drawing a little line. An equilateral triangle, all sides have the same length, which means that each angle measures 60 degrees because all three angles are equal and their sum has to be 180. Scalene triangle doesn't have any two sides that are equal in length. Similar triangles. Similar figures have the same shape, but they may not be the same size. In similar triangles, the angles are equal, but the sides may or not be the same length. Corresponding angles are angles that have the same measure in the two similar triangles. Corresponding sides are the sides opposite the corresponding angles. So this shows us two similar triangles. They look the same, but one is smaller than the other. So this is triangle ABC. The smaller triangle is DEF. They're similar. You can see that the measure of each side of the smaller triangle is half the measure of the corresponding side of the other triangle. However, the angles are equal. Angle A is equal to angle D, angle C is equal to angle F, and angle B is equal to angle E. The corresponding sides would be AC, which is the one shown in red, is equal to DF, also shown in red or purple or whatever that is. AB, which are blue, the side is blue, is corresponding to DE, which is blue. And the side BC, which is black, is corresponding to EF, which is black. This example uses similar triangles. And these are similar triangles, although they have an intersecting point. We want to find the missing length, x. Because the triangles are similar, their corresponding sides are proportional. So we can write a proportion. We know that this side is 5 inches, and it corresponds to this side that is 8 inches. Because you see where the angle is, the corresponding angle is indicated by the little hash mark on the angle symbol, the arc. So the sides opposite those equal angles are corresponding. So 5 is to 8 as 7 is to x. We want to solve for x. We can cross multiply. 5 times x is 5x. 8 times 7 is 56. Divide both sides by 5 because you want to solve for x. That gives us x is equal to 11.2. So that tells us that the value of x is 11.2 inches. Next, the Pythagorean theorem. This states that the sum of the squares of the lengths of the legs of a right triangle equals the square of the length of the hypotenuse. The legs are the two rays that go out from the right angle. The hypotenuse is opposite the right angle. If the legs have lengths A and B, and the hypotenuse has length C, then A squared plus B squared is equal to C squared. And you can see that they have actually drawn squares on here. They have, one side is 3, so the area would be 9. 3 squared is 9. One side is 4. The square is 16. And over here for the 5, the square is 25. And 9 plus 16 is equal to 25. Example 4, we're going to use the Pythagorean theorem. Find the length of the hypotenuse C on this right triangle. We have 9 and we have 12. We're going to let A be 9 and B be 12. So C squared is equal to A squared plus B squared. We're going to substitute our values in, 9 squared and 12 squared. 9 squared is 81, 12 squared is 144. So C squared is equal to 225. Now don't stop there. You have to find the square root of each of these. The square root of C squared is C. The square root of 225 happens to be 15. Sometimes the answer will be a decimal, but for this particular one, 15 times 15 is 225. So this one turns out nicely. And that is the end of this particular section.